with with the second talk of the day by Professor Hervé Queffélec from University of Lille, who will talk on weighted Hardy spaces and their composition operators. Go ahead, Hervé.
Yeah, okay. So first of all, I would like to thank the organizers, and especially Javad, for inviting me to this huge meeting where I already learned plenty of things. So this is joint work with my usual mates, Pascal Lefebvre, Daniel Lee, and Luis Rodriguez Pazza from Seville. And yeah, I already, so I cannot proceed. Why is that? So I don't succeed to continue. So what should I do?
All right.
Try to click on the slide.
Yeah, I click on the slide. Ah, yeah, okay. Sorry. So this work deals with the boundedness of composition operators, C5, which are formally defined by F goes to F composed with phi, where phi is an analytic self-map of the unit disk. And maybe you have already heard plenty of things in the course of Javad, but so let me apologize for repeating eventually things which you know well. And the set of such phi, such analytic self-map, we call it S, a set of symbols. And we would denote by S naught the set of those symbols which vanish at the origin, which plays quite an important role in this talk. And we will say that F composed with phi is subordinate to F using the terminology of Littlewood when phi is in S naught. Okay, and I just mentioned that we have this abelian semigroup property, which is written here. So the composition of two composition operators is again a composition operators, but with this twist in the order. This is trivial, but very useful. And here, C phi will act on the weighted Hilbert spaces of analytic functions, which are defined below. So you take the functions whose Taylor coefficient satisfy this square summability condition with a weight beta n. And well, I assume that this limit n for beta n to the 1 over n is larger than 1. Why is that? So, you know, sub-exponential decay of the weights. Yeah, and this is designed for H2 beta to inject continuously in the Frechet space of all holomorphic functions on D. And this Hilbert space has an orthonormal basis Z n over square root of beta n, normalized monomials. And well, for examples, you have the Dirichlet space, which you are probably very familiar with now. So dA is the normalized area measure as usual. And here, the weight, you have an integral representation for the norm, implying the derivative of the function, and the weight is written here. The norm in the Bergman space, which is a companion to the Dirichlet space, is given that way. And well, the beta n are written here. And an important point is that for Bergman spaces, the sequence of weights is completely monotone. And this is much easier. Well, I give now I switch to Littlewood subordination principle. You take all the beta n equal to 1, that is, you have the usual Hardy space H2. I recall that if phi is in S naught, so phi of 0 is 0, then phi is a contraction of H2 to itself. In equivalent terms, this matrix is infinite matrix AMN, the matrix of Taylor coefficients of the powers of phi has norm less than 1, indeed equal to 1 on the space little L2, which is obvious. And in Littlewood's paper, which is very dense and very deep, even if it is nearly 1 century old, Littlewood does not consider the case of composition operators with phi of 0 different from 0. So this can be done here. I recall that if you have an automorphism like that, phi A, then C phi A mates H2 to itself, and we can compute exactly the norm of C phi A. And you know, in Shapiro's book or in Cohen-McClure's book, this is proved in detail in Cohen-McClure's book, rather shortly in Shapiro's book, but it is not, the theorem is not attributed to somebody precise. And indeed, the two theorems, even if this, which I call folklore theorem, is quite easy to prove, simpler than Littlewood's one, it has a separate proof. And then once you know those two theorems, NFI in S can be written like this. And so, well, we know that this proves that every composition operator from H2 to itself is bounded. The proofs are different for Littlewood. I recall that if I is in S0, you have this identity where B is the backward shift just mentioned in previous talks, and M phi is multiplication by phi. So you have this orthogonal sum, and you get that the norm of C phi square is less than blah, blah, blah. And indeed, this is what is called for by experts the Moret-Pizier's interpolation principle. We saw, by the way, one example of this principle yesterday in the talk of Professor Pelaez, when he proved that, when he showed that T to the n was dominated by T to the n minus 1, to get that T was bounded. And this is the same here. In any case, if f is a polynomial of degree less than n, we get this. So we have the proof for polynomials, and of course by approximation for all functions on H2. And for what I call the folklore theorem, the proof is different. If you formally consider C phi star C phi, you see a Toeplitz matrix appearing, and as you know, every Toeplitz matrix has a symbol. Here, the symbol is a Poisson kernel at A, and indeed this works for every inner function with phi of 0 equal to A via this identity. And in any case, integral representations play an important role. But well, these were reminders. And I wanted to mention that here is a self-improvement of Littlewood's result. If I is in S0, and if J is subordinate to F, then we know that the sum of the squares of the BK is less than the corresponding sum for the AK. But indeed, this is true for all partial sums, you know, and the proof is really very simple, but useful. You just consider the operator of nth partial sum, S sub n, and then thanks to phi of 0 equal to 0, we have that Sn of j is Sn C phi Sn f, quite easy to check. And then since we know that C phi is a contraction of C node, S node, and Sn as well, we get exactly what we want. And as a corollary, Colzin observed that if beta n is non-increasing and phi in S node, then the result of Littlewood extends. C phi is a contraction from H2 beta to beta. This is just Rogozinski plus an Abel summation. It is obvious, but useful. And so sorry, the bottom of my slide is hidden. But what I can say is that what happens if phi of 0 is not equal to 0, or if beta n is not increasing, this will be the purpose of this talk. And here is a list of the difficulties you can face. it can happen that all the C phi A corresponding to automorphisms are bounded. For example, this is the case for the Dirichlet space corresponding to the weight n+1. And even in some sense, they are isometric on my space, my Dirichlet space D. And indeed, Arazi, Fischer, and Petre studied in depth the case of all semi-normed spaces for which you have this isometric property. So there is a Dirichlet space. There are also spaces like H infinity, BMO, etc. But I don't insist on that. Anyway, in my case, the beta n will be bounded above because if I assume that all composition operators are bounded, I have this inclusion. I have this inclusion, and then I have a constant C coming from the closed graph theorem. So beta n, which is the norm of s to the power n h squared, is less than C. So I will consider in the sequel always bounded sequences, and the Dirichlet space will not be later considered. If beta is non-increasing, the boundedness of C phi boils down to that of the C phi A because of the Golusin theorem we saw before. And so we might think things are quite easy, but even so, some C phi A can be unbounded on H. For example, if you take this sub-exponential weight x power minus square root of n, which is in our context, Critte-McClure observed that C phi A are unbounded. And more generally, we could prove the following. If you fix an A, if you want these composition operators to be bounded, then the norm of the reproducing kernel has to have at most polynomial growth. Equivalently, the beta n have to have at most polynomial decay. And we will see that it is not, this necessary condition is not sufficient. And this is the purpose of the rest. And I will present in this talk necessary and sufficient conditions for the boundedness of all C phi, where we are able to do that when beta n is essentially decreasing. But you can, meaning that, you know, if m is bigger than n, beta m is less, maybe not than beta n, but than a constant times beta n. But then the sequence beta n tilde is equivalent to the sequence beta n. It is, of course, decreasing by definition, or non-increasing, an English way of saying things. And this is what we will mostly assume without loss of generality. So we will give a definition. The non-increasing sequence beta n has a delta 2 property, which is reminiscent of what happens in Orlick's spaces if we have this inequality. So beta 2n, which is supposed to be less than beta n because my sequence is decreasing, is yet larger than delta times beta n. Of course, delta is a fixed positive constant. And this condition can be thought of as a slow oscillation condition. The quotient says that m is larger than n, but then the quotient beta m over beta n is bounded below, by the way, by something which depends only on m over n. So this is the way we should see things. And this is strictly stronger than polynomial decay. It implies polynomial decay, quite easy to see, but it is strictly stronger. And now here are our 4 theorems. And in the first two, I will assume that beta is non-increasing. So the first theorem is quite simple. This delta 2 condition is sufficient for the boundedness of all C phi from H to itself. And the second theorem, this delta 2 condition is necessary. So why to enunciate those 2 theorems separately, and why not say this condition is necessary and sufficient? Let us say it is because the proofs are completely different and based on different ideas. And now what about decreasing? if we start from a general sequence, this sequence will be essentially decreasing, if and only if all the composition operators corresponding to symbols vanishing at the origin are bounded. And so if one wishes, our theorems answer the question. So you start from a weight as in our general presentation to satisfying this sub-exponential decay. The following are equivalent. Beta is essentially decreasing and has delta 2. And all C phi are bounded with, moreover, they are moreover uniformly bounded on S naught. But the theorem 4 to come indicates that the situation will be more intricate than we might have expected, than we expected at the beginning, by the way. You might think of a bear trick, you know, if all C phi with phi in S naught are finite, we might think by an abstract nonsense of a functional analysis, the supremum is automatically finite as well, Banach-Stein house or something like that. And it is not the case. And indeed, we have the following theorem. We assume that beta has polynomial decay. We know that this is anyway necessary. And this weird condition, if you wish, for every delta positive, you can find a constant C delta such that beta m is less than C delta beta m whenever m is much larger than n, 1 plus delta m. And in that case, we have that condition. All the C phi are bounded for phi in S naught, but this can happen with the supremum being infinite and with, of course, non-essentially decreasing beta. And concerning the assumptions, it means that beta can oscillate, but not when the two indices m and n are far apart. You see, this is what is written here. And what about this delta? It will turn out in the proof that each phi in S naught will generate its own delta and C delta. So we see that. And now I give sketchy proofs of some theorems. And I will insist on two aspects. The use of the stationary phase method, reminiscent of the van der Korput inequalities, and the use a result of Katsnelson, not the Katsnelson of harmonic analysis. It's Victor Katsnelson, a Ukrainian mathematician, and I will enunciate his result shortly. And this result was already exploited by Chalanda and Partington, more recently by ourselves in a paper which involves approximation numbers, but I will not talk about approximation numbers today. And I will rather discuss in the second part a result of unconditional multipliers, whose proof uses Katsnelson result. And the difficulty in all that follows is that we have no integral representation for beta. So essentially, we assume beta n decreasing, okay, but not completely monotone. That is to say, we have no integral representation for beta n, and we have to work differently. And so now I will not prove theorem 1, and I go to theorem 2. So I try to prove that this delta 2 condition is necessary for the boundedness of all my C phi. And then I need to, here is a statement which looks very technical. So we want to estimate this oscillatory integral I, whose sum from A to B of exponential of I f of x dx. Here, f is a real valued function, regular C3 function. It has a single critical point inside AB. And this critical point is deeply inside AB, if I may say. So you have assumption 1. On this small interval around the critical point, the second derivative is bounded below. And globally, on the whole of AB, the third derivative is bounded above. And then we have this estimate which is a variation of a lemma you can find in Titchmarsh's book, but we gave an independent proof and we slightly modified the assumptions because this is what we were needing. And so you have this, and I don't know, yeah. And you see what is important is you can forget the error term and you control the modulus, C1 over the second derivative of f at C1/2, and the argument of this oscillatory integral. This is what we will use later. Now, if we specialize to our situation, we consider, well, these automorphisms, these hyperbolic automorphisms. We raise it at the power n, and we consider so the Taylor coefficients AMN of the nth power of an automorphism. And we can write TA is an inner function, so we write it like that. HA is a primitive, say, of the Poisson kernel at -a, and it is an odd function since pi a is an even function on -p plus p, so that by the Fourier formula, we can write the AMN, which we want to estimate like that. Or if you prefer, the I and they appear as a real part of an integral to which I can apply the previous slide. So you see that the function capital F, NHA minus MX, depends on M, on N and M. So we might expect that the behavior will highly depend on the relative position of N and M, and this is the case. And this is what we obtain. We obtain a precise estimate of this integral when, because we can do some estimates and we find that. So an error term, n to the -3/5, a main term, because the main term will have size about n to the -1/2, and an argument which we, so sorry, the bottom part is invisible. But let me say that we can control the variation of data. It varies slowly and regularly, like the nth root of unity. And so this control of an IMN will be sufficient to give us a control of the modulus of AMN. And anyway, here is the lemma we will use. We can find a fixed parameter delta such that you have a block, an interval, by the way, of integers, which is of size approximately n, which is neatly on the left of n. All the elements are less than 1 minus delta n, and on which we have a good lower bound for the AMN. So it looks very specialized and very strange, but I should say that this behavior is very irregular of this coefficient depending on n. N, if you fix n, the sum of AMN squares with respect to m is 1. This is just Parseval's for the inner function phi to the n. The supremum is less than n to the -1/3, and this is, by the way, optimal. And you have experts on this, who are Oleg Zer and Rachid Zarouf, and there is a more recent paper by Borichev, Fouché, and Zarouf, which gives a complete and rather sophisticated picture of the behavior of AMN according to the relative position of M and N. And they use notably the Airy function. And I mentioned that Yves Meyer also recently used the second estimate, AMN less than n to the -1/3, in a paper which is completely unrelated on crystalline measures and mean periodic functions. So it seems that the estimation of these Fourier coefficients or this AMN intervenes in various situations. It was the case for Zer and Zarouf and it is the case for Meyer and also for us. And anyway, we don't need such a sophisticated version, and we just use this self-contained lemma in the sequel. And now, how can we prove the necessity of our condition? We write again that phi n of z is the sum over m of amn zm. And now this sum on the left is just the norm of phi n, which is c phi of zn. And since we assumed that this was bounded, we get this inequality, c squared beta n. We read this inequality the other way around, so c squared beta n is larger than that. And if I sum only on the block Gn, of course, this is smaller. And on the block Gn, I know that beta sub m is about, I know that amn squared is about n to the minus 1, which is 1 over Gn, since Gn has about n elements. And I guess I get these necessary conditions. Beta n has to be larger than this average over the block Gn. Well, and if beta is non-increasing, we get this condition. And this condition, you know, beta n bigger than some constant beta 1 minus delta n is exactly the delta 2 condition. So this condition is necessary when beta is decreasing. And I mentioned in passing that instead of automorphism like the T sub A, we could have used these singular inner functions, which are here, because we have a theorem which is a precise version of the theorem of Zege. So it's very technical. Let me just indicate, and then the Taylor coefficient C sub m of A depend on the Laguerre polynomial of parameter minus 1. And as you can see, we control, say, the modulus of Cm of A, and there is an argument d square root of Am plus pi over 4, which is very complicated, as it was before for automorphisms. And in any case, this gives again the necessity of the condition. And I mentioned that a weaker form of this lemma was used in an old but very nice paper by Shapiro and Newman on the Fourier on the Taylor coefficients of inner functions. And now I switch to an intermediate result of Katsnelson, which I already mentioned, which is the following. You have a Hilbert space with a privileged orthonormal basis E sub n, and you have a bounded operator whose matrix on this basis is Amn, and you have an arbitrary sequence of positive numbers, and you consider the diagonal operator associated. And this operator is formally defined. You know, it's not bounded because we make no assumptions on the D sub n, they are generally unbounded. And we only make the assumption which is here. If dm is less than dn, then amn is 0. This assumption should be thought of as an assumption of lower triangularity for the matrix A. So the matrix A is lower triangular with respect to the order induced by the dn. And then the conclusion is that d minus 1 td is again bounded, even if d and d minus 1 were not, and with this inequality on the norm. So it seems quite simple. The initial proof of Katsnelson was with increasing sequence, and then AMN really lower triangular. We need this form, and the proof is exactly the same, by the way. And well, the assumption is met by our composition operators, acting either on H2, so with abuse of notations, I write it T on H2 and D minus 1 TD on H2 of beta as soon as phi of 0 is equal to 0. And a word about the proof. The proof is one line, by the way. You consider this function. You could tell me, but this function is certainly not yet defined. But you can assume that H is finite dimensional because then you will make a limiting argument. And so everything is defined. And you consider this function in the right half plane, which is an unbounded open set. But this function is bounded on this set, and it is subharmonic. So we have a maximum principle for subharmonic functions in dimension 2 on even unbounded domains. On the boundary, you know, if Z is IY, U of IY is norm of T. Why? It is because, anyway, the D to the IY is a unitary operator, whatever the dn's are. So the fact that we take an imaginary power erases all the problems of growth of dn, and we have this. And U of 1 is what we want to estimate, and that you just say that U of 1 is less than what happens in the boundary, and you have your result. Let me give a baby example. So you take a 2 by 2 matrix. So this matrix is lower triangular. You take D diagonal matrix with D1 less than D2, and then D minus 1 T8D is just T with a change of parameter, A D1 over D2. And you can check in various ways that the norm of TA is an increasing function of A. But yet you see the expression of the norm of TA is not so simple. But anyway, so we have this example which does not use Katsnelson's principle, but which just shows that the situation is maybe not so simple as that. So now I pass to my theorem 4, and I assume that beta has polynomial decay. So this is just a reminder of my theorem, and we'll see how the proof goes. So we start from phi in S naught, and believe me, for the moment, then this phi produces a delta and a C delta, which are positive constants. And the point is, we change our weight now. We take this weight, gamma n, the max of beta n, and this supremum. And the point is that, of course, gamma n is equivalent to beta n. So indeed, the two spaces H2 of beta and H2 of gamma are the same. And the main point is this inequality. If m is much larger than n, then gamma m is less than or equal to gamma n without any constant. We will see later how it works. And so, we have implied matrices, but it will be repeated on the next slide. And we first need the Cauchy, by the Cauchy inequalities and the Schwarz lemma, we have that if we have this inequality. AMN is smaller than this quantity. And the only thing is that, we assume that phi is in S naught and is not a rotation. The case of a rotation is trivial and can be handled directly by hand. And in that case, we have this inequality. The only thing which matters is that the coefficient of n, 1 plus rho, is strictly larger than the coefficient of m. And then we take delta is rho over 2 with this rho, and we split our matrix in two blocks. So A1 plus A2. The block above the diagonal, if I may say, for A1, and the block below the diagonal for A2. And indeed, A2 is super lower triangular because it lives not only on the pairs Mn with m larger than n, but with m larger than 1 plus delta n. And we do a similar thing with the matrix BMN, which corresponds to the matrix of my operator on H2 gamma. And I know that A is bounded. I want to deduce that B is bounded as well on little L2. Now thinking in terms of matrices. And okay. And this is what is recalled here, maybe in a more precise way. So you see B is D minus 1 AD, where D is this diagonal operator corresponding to 1 over square root of gamma. So you have to believe me for that. And we prove first that A1, the part above the diagonal, is Hilbert-Schmidt, meaning that all the squares of all elements are finite. The sum of those squares is finite, and B1 as well. And this comes from the lemma, because AMN is very small for M not much bigger than N, and gamma M over gamma N has no influence because we have this polynomial decay assumption. Then A2 is, of course, bounded, because we know that A was bounded, Littlewood's principle, if you wish. And the point is that B2 is bounded as well, and this will follow from Katsnelson. Let us take it for granted for a second, and then B is B1 plus B2 is bounded. So we have our theorem, and now the key point is that if I recall what was formed, this is this inequality, and now we can use Katsnelson for A2, because if dm is less than dn, then gamma m is larger than gamma n. We have so we have m less than that, because in the opposite case, gamma m would be less than or equal to gamma n, which means exactly by the definition of the matrix A2 that AMN2 is 0. So we have our theorem. And as for a counterexample, we can take blocks of factorials like that and define beta n is, well, 1 over k factorial on all the block except on the point of index n is k plus 1 factorial minus 1, on which it drops brutally and then instantly goes back to its initial value. And this sequence is not essentially decreasing, of course, because you see beta n plus 1 over beta n tends to infinity for n equal to that value. It has polynomial decay because we can check very easily that it is larger than 1 over n plus 1. The factorials are there for that. And moreover, beta m is less than beta n as soon as m is larger than n plus 2. So as soon as m is slightly larger than n, we have this decreasing condition. And so we can apply theorem 4. And of course, in that case, so C phi is bounded for all phi in S naught, but the supremum is infinite, because if it were not, we would have that the sequence beta is decreasing, which it is not. And so, okay. And I should mention that in that example, no C phi A is bounded, because we know that we have this necessary condition, and this necessary condition is violated for n equal to k plus 1 factorial minus 1. You see in this inequality, the left-hand side is 1 over k plus 1 factorial, while the right-hand side is average of numbers all equal to 1 over k factorial is 1 over k factorial, so it's much bigger. So you see the situation can be complicated when you don't assume the sequence to be decreasing or having slow oscillation. And by the way, we don't know completely what is a general picture. And now I switch to something else for the 10 minutes which remain. And I give one more application of Katsnelson's theorem to a multiplier problem. So as you know, the set of multipliers of an analytic Hilbert space is the set of functions W such that when you multiply f by W, you remain in H. And we mostly have that M of H is H infinity for the Bergman spaces of Hardy spaces, not for the Dirichlet space. And for the study of composition of weighted composition operators, which are composition operators followed by the multiplication by a function W. So T of F is that. We need a conditional version of M of H, which is this one. M of H phi is the set of W such that W times F composed with phi is in H for all F in H. And when C phi maps H to itself, which will be the case with our admissible weights, we have the double inclusion. M of H phi is something between M of H, mostly H infinity, and H. Of course, M of H phi is included in H because if you take a multiplier W in that set, a W is, by definition, MW C phi of 1, and so 1 is in H and W as well. And we want to study the extreme cases in that inclusion, and we first going rapidly a definition. We would say that my space is admissible only if it injects in H, if H2, sorry, injects in H, and C phi, if C phi is bounded on H for all automorphisms. This forbids the weight x of minus square root of n. But anyway, we are in the situation where the multipliers are H infinity by Katsnelson's result. I am quick on that. And here is the theorem we have. This theorem is due in the H2 case to Atelier and then Contreras and Hernandez-Diaz. So you have an admissible Hilbert space, symbol phi, and then we have this inclusion. So this is new. And the space of conditional multipliers is as large as possible if and only if the symbol has subnorm less than 1. And this space of conditional multipliers is as small as possible if and only if phi is a finite Blaschke product. So this is the extension, you know, of this result of Atelier, Contreras, and Hernandez-Diaz to the more general case of admissible Hilbert spaces. And let me start. This is a reminder with the implication from left to right in the third statement. So if I denote by W up the norm of this weighted composition operators on H2, we have this estimate. We are on H2, so K is Bergman kernel of H2, and we have this estimate. So that if M of H2 phi is as small as possible, by the closed graph theorem, we have an inequality of this type, which will lead us to this condition. But let me first show how it works for the upper bound of the up norm of K sub A. So let me call B equal to phi of A. And we use here a kind of a happy identity. 1 minus A square, Ka square is a norm of the derivative of automorphism phi A. And also we will see that this symbol phi B, phi A is in S node by definition. 0 goes to A, goes to B, and phi B brings back things to 0. And so by this happy identity, we have this. I added phi A composed with phi A. Anyway, phi A is involutive, so it makes no difference. But then, by a change of variable, you get this. Then you inject phi b times phi b, and you see at the end phi b phi a is in S naught. So this is less than that, and hopefully, yeah. And then you use what I call folklore theorem to dominate this by 1 plus b over 1 minus b, the norm of F2. And for the last statement, so I have this inequality, and I read it by the estimation of Ka up and the fact that Ka infinity is just that, like that. And then you simplify and you exactly get this condition. But this condition, as you know, characterizes a set of finite Blaschke product. And more precisely, if you have a finite Blaschke product, you have this condition, implying in particular that mod of phi a tends to 1. And if we only assume that mod of phi a tends to 1, but in an unrestricted way as a tends to 1, phi is a fine Blaschke product. Indeed, in the work of Contreras and Hernandez-Diaz, they observed that it would be sufficient to assume m of h2 phi included on HP for some p bigger than 2, and we could even weaken this assumption in terms of Orlick spaces, but I will not dwell on that. And now I pass to the proof of this inclusion. And this inclusion will provide that if m of h phi is small, then phi is a finite Blaschke product. I have no longer my happy identity, but I have this inclusion due to Katsnelson. And so if m of h phi is as small as possible, same for m of h2 phi, but then I know that phi is a finite Blaschke product. And so how to prove this inclusion? We first assume that phi of 0 is 0. We take a multiplier of m of h2 phi, and then we apply Katsnelson for this operator, mwc phi. And we are allowed to do so because if I consider En the canonical basis of H2 and this scalar product for n less than n, well, Ten Em is by definition W phi n Em. And you know, since phi of 0 is equal to 0, the first term in W phi n can only be something like a constant times z to the n, and so it will be orthogonal to Em if m is less than n. So using that, we get our inclusion. And in the general case, we just perform a Forstmann shift. We consider this phi a. And our admissibility assumption implies that, of course, H2 is admissible. So we have this first equality because C phi A maps H2 to H2. Then we know in that case that we have that inclusion. And again, M of H phi A composed with phi is nothing but M of H phi because C phi A is bounded on H. This was our assumption. And the rest is now fairly easy. And anyway, my time is nearly over. I will just mention, if you permit, some open question. Is there a complex variable free proof of Katsnelson's result? Well, Katsnelson's result seems so elementary to enunciate with only real numbers, if one wishes. Why are we forced to let subharmonic functions intervene? Well, and anyway, the result, well, let's completely the behavior of the Dn disappear, because on the boundary we have Dn to an imaginary power, so Dn plays no role. This is not completely satisfactory. There's a theorem of Grothendieck, which implies the famous Grothendieck constant, which describes the Schur multipliers of bounded matrices. That is to say, if a matrix is bounded on little L2, then if you multiply term by term, so show product, you get again a bounded operator. And the Grothendieck's theorem is that then, well, exactly, lambda mn has to be to the form scalar product of xm yn, where xm yn are bounded vectors in some Hilbert space. And we would like to, here we see that Katsnelson's result says that this is a show multiplier of lower triangular bounded matrices. Could we hope for a full characterization of show multipliers for those matrices? Here we use a very special additional assumptions on this band. And we saw that the slow oscillation of this sequence is in some sense a necessary and sufficient condition. But theorem 4 showed us that the situation was more complicated. So we're in the case where beta n is not slowly oscillating, we don't know. And here are some references, and well, my time is over, so thank you for your attention. This is all that I wanted to say.
So let's thank the speaker. So thank you. All right, so any comments or questions, either put them in the chat or just shout out your answers or your questions, actually. All right, I don't see anybody trying to monitor everything. All right, so if anybody has any questions, I'm sure they can contact Hervé on their own. So let's thank him again for his nice talk on weighted composition operators. All right, so we have a couple minutes until the next